just going from a furnace to a heat pump, you're losing some restrictions, some stuff that's in the way of the air.
If you swap over to a heat pump, suddenly that ductwork might perform way better because we have a lot less things.
Better for sure, right? Way better. It depends, right? And it depends on what the problems are.
Welcome back, Alex Meany. Alex is the person that I go to when I want to level up on my ability to do HVAC design calculations. Thank you very much for coming.
It is my pleasure as always.
Okay, so what I'd like to talk about is, we got a lot of feedback from the first couple of videos. If you have not seen those videos, we did a deep dive on Manual J, deep dive on Manual S. And one of the things that you said is, don't use some of the data that's like the most available.
Yeah.
They have hidden extra data, which we heard back from a bunch of people. They're like, I can't find it. They won't give it to me.
It is hard.
Okay.
And
you are yelling at them.
Yes. Literally gave a presentation at a HVAC symposium, made the camera get up in here as, you can't do this, and complain if something goes wrong, right? Mm-hmm. We're not giving you the tools. We're not going to do it right? The right tool, right job, all that stuff.
Cool.
You can typically, if I was maybe not a homeowner, but if I was an HVAC guy, if I was a building science guy and I wanted to get access to this stuff, one of the best places to start is probably a local distributor, right? Because they typically give this information to contractors, whether they know it or not, right? Mm. It's in there. The biggest problem for a lot of us is it's behind a password wall, right? Like, it's not out in the open. It's not available to everybody. There's a you've got to get through this thing to get to it. And it can still be hard to find when you get there, but getting beyond that password wall can be difficult. And a local distributor is often a good place to start to get that.
Nice. Okay. Now, I've been asked, because we've been talking a lot about new construction stuff, and existing homes are a major thing. We got to talk about it. My parents have an existing home that we've been improving, and there's an entire playlist about that. And so one of the things that I wanted to bring to you is, my parents were like, hey, our furnace is like a little old, and so we're thinking about getting a switch. They're literally in our backyard here in Atlanta. Furnace with an air conditioning coil. And that's two different pieces of equipment. The blower, the air handler, which is the fan that handles the whole thing, is inside the furnace cabinet. And then the coil is separate. So I was like, well, they said, should we go to a heat pump instead? And I said, well, number one, a heat pump is like 300% efficient often. So that's a nice thing.
Yep.
And they said, how is that? That's the topic for a different video. But my thing is, number one, if we had air handlers nowadays, modern air handlers, like, for example, a Mitsubishi, which can handle up to 0.8 inches of water column of static pressure, that could deal with the fact that we have this ductwork that is just there. Like, you're not going to replace the ductwork. So doing all kinds of duct designs is kind of beside the point. But if I was to do that, would that be an extra benefit to the first benefit, which is that I'm taking this system that's got two different pieces of equipment and then combining them into a heat pump where I have less things in the way of the airflow?
Sort of. I'm going to go with sort of. You've heard the expression, just because you can doesn't mean you should.
Okay.
Yeah. 0.8 is just because you can doesn't mean you should. It might be, but it probably predates that. Because these fans are capable of withstanding more resistance. Cool. But it takes a toll, right? Not to get crazy technical, but when you had the old style of fan and you had more resistance, the amount of electricity they drew went down because they were moving less air, and it was not changing the speed of the fan. The blower was, this is how fast I go, right? And if I put a lot of air in that, I'm going to have to lift a lot of that air. Air weighs something, right? If not a lot of air goes through it, I'm spinning the same speed, but I'm not lifting as much material, not as much air. And so it actually reduced the amount of energy it used, right? I'm not saying it was good for the thing, but it didn't have these major consequences. Our modern constant air volume, constant torque motors, when you put more resistance on them, they will work harder, right? They will rise to the level of the equipment, whether it's air volume or torque. They will spin faster. They will work harder. They will use more electricity, and that's not necessarily good, right? They were designed to operate within this spec, and when it's capable of getting outside of that, okay, but there's going to be wear and tear costs. There's going to be energy costs. There's going to be, it's one of the more insidious problems in the HVAC industry, because it's not a problem that shows up right after the guy leaves, right? it seems to be working fine. And son of a gun, I had to replace it in 7 years. These things usually last a little longer. I wonder why that was.
They sold the house before then.
A lot of times that's true. But so it can be a problem. But changing out a piece of equipment is an opportunity, right? There is a lot going on just connecting that system to the ductwork. Okay. How big is the inlet? How big is the outlet? What is it shaped like? How aerodynamic is it? Can I make changes to that? It can be difficult sometimes. A lot of equipment's getting bigger, so I'm not exactly creating more room. So depending on where it is, it might not be so easy.
And just to clarify, it's getting bigger so that it can be more efficient while doing basically the same job.
Yeah.
Right? Okay,
yep.
Cool. Like big enough that you can't even fit it up through an attic hatch, for example?
Will sometimes happen, but they have often solutions to that. They come in pieces and you can get them up there. They make smaller ones that aren't as efficient, but one of the big things that just going from a furnace to a heat pump is you're losing some restrictions, some stuff that's in the way of the air. If I have a furnace and a coil, what I have is a heat exchanger and a coil is a type of heat exchanger. It's going in the other direction, but it's exchanging heat. So now I have 2 heat exchangers. Go far enough north, and now I have a 90% furnace. I have 2 heat exchangers in the furnace, and now I got 3. You convert that to a heat pump, you have a coil. You may also have some electric resistance heat in there, but it's like the squiggly little wires about this big, right?
So they don't have any.
There's a little bit of resistance, but it's tiny.
And let me just clarify for the audience here. I'm talking about total external static pressure. And if you don't know that, there's a video I'm linking on screen right now to explain what that works. But it's basically all the pressure that's external to the equipment that contains the fan.
Yeah.
So in the case of adding the coil, in any case, if you're adding a coil, it's external now.
That's right.
So essentially with a stuck system that might be a terrible performer with a furnace, especially a high efficiency furnace and an air conditioner, if you swap over to a heat pump, suddenly that ductwork might perform way better because we have a lot less things.
Better for sure, right? Way better. It depends, right? And it depends on what the problems are. It's not always the coil if it's old enough. But with a lot of newer systems, you would see an improvement there. And like we were saying earlier, you're not just replacing the box, right? The connections to it are also part of this, right? So what you often have is not enough return air. You have too small filter, right? I got the filter that fit on the cabinet. Good, sweet. It says right there on the box, 0.1 inches of pressure drop. Yeah, when the air is moving about 200 to 300 feet per minute. If Ford got to test their gas mileage and pick the size of the hill they drove it down, they could always hit the gas mileage numbers. Well, when the filter manufacturers get to pick the velocity they test their filters at, when they publish that pressure drop number, that's exactly what they're doing.
Wait a minute. Okay, I want to. So Aprilaire is something that I spec a lot.
Oh, I love their stuff.
So they test at the right.
Well, and one of the reasons I love their stuff, they tested all of the airflows. Well, not all of the airflows, but all the ones that would make sense.
Okay.
They have a chart.
Great.
How much airflow? How much pressure loss? Right. Some of the, I don't know why. I'm not going to guess it. Why? I don't want to throw any shade here, but they publish a number, and that number tends to be 0.1 and 0.08. The old school size.
Very fishy.
Those are numbers that have been kicking around the HVAC industry.
Not even 0.10.
Yep, 0.1 and 0.08. Because those are well, I don't know if it's because, but it just so happens those are numbers that have been kicking around the HVAC industry and the duct design world for a long time. I am of the opinion that they picked the airflow that hits those numbers so it doesn't raise any red flags, right? People look at that number, they go, I recognize that. That's a duct number. Sure, that's normal. And they move on with their day.
So returns being too small. Normally your return is like the biggest duct that you've got. And that's mostly if you have a central return, which I have a central return in this house.
Most systems do.
When they're going to upsize the return, what I'll see them often do is take the return that's there, that's the thing that's too small, and they'll cut a hole in the side of it. That's the most restrictive part. You need to
it still reduces the pressure.
Fair enough.
It's not about, so if a lot of people, and I used to think this, that when you have airflow, it's about the size of the hole. And a certain amount of air is going to come out the size of that hole. Nope. It's about the total resistance of the path, right? And so if I have a very long run and I have a 5-inch hole, I will get a very different amount of air out of that than if I have a very short run and a 5-inch hole, even at the same spot, right? And so the size of the hole it plays a role in that, but it's only a part of the overall amount of restriction.
That's a good point.
And so there are things that you can, especially when you're dealing with a non-ideal situation. I inherited this problem. This is what I can fit. Improvement's improvement, right? So it's not always necessarily a bad thing.
And I think that that's an interesting point, is that like you do it in stages. Whenever you're making improvements, you just try something and you test it. And if testing means you just live with it for a month or a season or a year or whatever, and then you're like, it's not good enough, and you do something else, and just like that staging, and then you'll kind of reach this point where you say, yep, good, I'm happy.
Yep.
Because nothing is perfect.
Yeah, no, yeah. And you bring up a good point that it's the reason a lot of, in my opinion, the reason a lot of return ducks are undersized is, here's the biggest one they make. Here's the biggest equipment they make. Well, those must go together. That is not how it works. If you look at even the wrong way to do it tells you that's not how it works, right? But it makes a certain sort of sense, right? There's this size hole in the thing. All right, I need that size hole.
Right.
No.
That goes for filters too, which is what I like. The Aprilaire, they've got these ones that are like a big filter, and then it has this collar that goes down to the size of your actual connection to the air handler, which is much, much smaller. And that's the idea, is like, don't just do what they say. That being said, the SEER 2 stuff, can you just briefly hit on how SEER 2 is changing the equipment landscape right now?
It didn't change it it's changing a lot of model numbers. It's changing the way things get rated. And so all the manufacturers are scrambling to run through that. It's trying to give a more accurate assessment of efficiency. And a lot of the changes they're implementing are actually just sort of prepping for the changes coming in the next generation and the next generation. And so it's hard to make a blanket statement about how SEER 2 is affecting things, other than you can't really do you can't do apples to apples comparisons of those SEER numbers anymore, because they changed the test, right? And that's really the biggest thing. Like, air conditioning didn't change. Right, it's the way they rate efficiency did, and it's because the way they were rating efficiency before was kind of a softball, right? It ain't exactly fast pitch yet either, but they did make it a little more realistic, a little more not difficult, but a little tougher. The biggest change was when they rated those fans. They used to be able to rate them with basically no ductwork, right? They used to be able to rate, it was like 0.1, I think, was the total resistance, the total external static pressure, which means the fan wasn't experiencing any significant resistance. And one of the reasons why they did that is because the types of motor we used to use, it didn't make that much difference, right? Now we have these ECM, constant torque, whatever, motors that, like I said, use more energy when you put more resistance on them. So when they were using these low resistance tests, these motors were overperforming, because that's not a realistic environment. And so they were getting an artificial boost to their efficiency. And now when we test their efficiency, we put them under more restriction that better mimics a real field condition. It's 0.5, and you know what you're seeing out there in the field in a lot of these existing systems. It's not a lot more than that in a lot of cases, but it's mostly about the efficiency rating.
And just to remind everybody, what Alex shared with us in one of the first videos that we shot in the series was that if you are buying a high SEER piece of equipment, often that is at the expense of the humidity control, because you can't have both ways. Engineering is a series of compromises.
Right. And cost is one of those compromises. So you kind of get both, but it's going to cost you.
Awesome.
Yeah.
Thank you very much for nerding out with us.
It's my pleasure.
I hope that you guys have enjoyed this. If you have questions about this like rambling, very cloudy conversation that we're going to keep on having with Alex, because it's just like there's a lot to talk about. Post the comments below. I'll deal with those directly. I'll bring Alex over to answer some of those too. Like and subscribe. Tune in next time.